So today we are going to talk about the fifth handout, which is algebraic connectivity. So one of the issue about the graph, or even more application like a social network or some other things like machine learning, is trying to do the following task. If you have a huge network, no matter what does that means. For example, if it is a social network, I believe you have seen this kind of graph. Like these three people are knowing each other very well. No, each line says that these two people know each other. Right? You can use the Facebook and being a friend of each other to draw a line of all the people all over the world. And then the question is, can you somehow partition the graph into two parts or several parts, saying, okay, this group of people, I think they are a group of friends, and somehow there is another group of people, they are friends. Okay, and so this idea is a little bit vague. By that I mean, of course, we know these three people, they are friends of each other, but these two people are also friends, right? Are you going to say that these four people are a group of friends, and how about these five people, right? This is too much, right? But these four seems okay. The thing is, it is a bit hard to really cut the graph precisely, putting it into two parts without any edge in between them. But there is some like loose area. By that I mean, for example, here only has one edge and one edge. If you can cut them, then it looks like, okay, this part seems okay. It is one part, this is another part. And this kind of question has no particular answer. But still, as a human being, you can kind of tell that, okay, these group of people, for example, support KMT, and that group of people support DPP. But you can still tell certain group of people, they have a certain friendship inside. Although the friendship is connected, right? I know you, you know that one knows that one. So basically, all the people all over the world belong to the same graph. There's just one connected component. So everything we are going to talk about from today, next week, and maybe 2 weeks later, it is talking about how to make a good partition of the graph, and it follows the same technique. And we will see how to do this. Okay, so let's go back to the graph theory a little bit, and so that we can dive into the application part. So let's start with theoretical and more concrete question. So before we start, in graph theory, we say a graph is connected if between every two vertices, there is a path connected them, right? So in this graph, it is connected, but if you take out one of the vertex, take out the central vertex, then if you view all of this as a graph, then we call this as a disconnected. Easy enough, right? So in graph theory, there is one term called connectivity. It is a measure to determine how connected it is. For example, we know this is connected, this is not connected, but somehow it seems like this one is super connected, right? It is a bit hard to take it apart. So talking about the connectivity is try to measure how connected it is. And here is the definition. It is a bit long. Okay, so the connectivity of a graph is the minimum number of vertices, so that we are going to remove that, and after removing it, the graph becomes disconnected. So let me finish writing. What I wrote is a little bit different from the handout, but they are basically of the same meaning. Okay, so let's try to analyze this long sentence a little bit. It is trying to define this new term. It's called the connectivity. Okay, so this new term, it is a number. It is the number of vertices, and it is the minimum number of vertices. So it is supposed to be an integer, and 0, 1, or 2. And what kind of vertices? If you pick some vertices and their removal, this is the noun of remove. Their removal will make the graph connected. Will make the graph disconnected. Then we say the minimum number of such vertices is called the connectivity. Okay, so give you some example. It will be easier than reading this long sentence. Okay, this graph, if you take out this particular vertex, then it is disconnected. So in this case, we say the connectivity is equal to 1. And I forgot to mention that this connectivity is denoted by kappa g. Okay, so kappa g of this graph is equal to 1 because you take out the single vertex at the middle, then it becomes disconnected. And how about this one? For disconnected graph, if you take out none of the vertices, kappa g is equal to 0. Because you don't have to take out any vertex, it is already disconnected. In contrast, you can do a bit more. For example, this one, it seems more connected than the one on the left. The reason is, if you just take out one vertex, whichever the vertex you took, it is still connected. However, if you take out two vertices at the same time, then you can make it disconnected. So the kappa of this graph is equal to 2. So I think that should be easy. At least the concept is easy. I'm not saying it's easy to calculate this value. You have to try a few vertices in order to understand, okay, this is the best. Now the first question arises. How about this one? If you take out this vertex, it is a K3, it is still connected. If you take out two vertices, it is a K2, it is still connected. So no matter how many vertices you take out, it is always connected. Right? So this definition does not apply to a graph that is complete. So in this case, we vacuously define the complete graph will have the connectivity n-1. In this case, it is 3. So Kn, it is the complete graph on n vertices, and the connectivity of this graph is n-1. We take out all the vertices until there is only one vertex left. So it doesn't make sense. It just vacuously we define it this way. Okay. Now, in this lesson, there is only one, maybe two key points, but let's make the definition about the title, the algebraic connectivity. Let's say G is a graph, and L is its Laplacian matrix. Okay, and so we can calculate the spectrum of L, which is equal to lambda 1 as the smallest one, lambda 2, and keep going. So it has n eigenvalues, and we're going to take out this lambda 2. Okay, so the definition says that lambda 2 as the algebraic connectivity of G. Okay, so this is a new term. And we will say just for convenience, we will denote it by lambda 2 of G. Okay, so the definition is easy enough. It is just calculating the eigenvalue and then take the second smallest one, and we call that as the algebraic connectivity. So you will see one of the main difference is this connectivity is not necessarily an integer, right? It's just an eigenvalue. There's no point that it has to be an integer. And indeed, there are lots of graphs whose algebraic connectivity it is not an integer. But what we call that as the connectivity, right? Previously, there's some reason, right? After taking out certain number of vertices, then it becomes disconnected. But now we just talk about a certain eigenvalue. So there should be some reason behind it. So here is a few reasons of why we call that as the algebraic connectivity. Before the first point, I want to recall some fact. Okay, recall that the nullity of L is equal to the number of components of G. This is what we learned at the very beginning when we start talking about the Laplacian matrix. So this means lambda 1 is always 0, and if it has 3 components, then lambda 1, lambda 2, lambda 3 are all equal to 0. And what does that mean is the following. It says that, how about this one? Lambda 2 is equal to 0. That means G has 2 or more components, which means it is disconnected. Okay, so lambda 2 equal to 0 means that G has at least two connected components. And this means G is disconnected. And similarly, because this is if and only if, you can just say that lambda 2, it has to be greater than 0, okay? It is not 0, that means G has only one component. And this means G is connected. Okay, so you can tell that from lambda 2, you can see whether the graph is connected or disconnected. So that's one of the simple reasons that it is called the algebraic connectivity, because you just look at lambda 2, then you know whether the graph is connected or not. But there is a more elegant or deep theory behind this parameter, which is the simple formula here. Lambda 2 is always a lower bound for the kappa 2 for any graph, except for k1. I don't really know what is the kappa of k1, so forget about that. But starting from k2 and starting from anything with at least 2 vertices, then this inequality holds. So basically that's all I wanted to say. This lambda 2 is called the algebraic connectivity because it is a lower bound for the vertex connectivity. And therefore, if you don't want to calculate the vertex connectivity, maybe you can just calculate the lambda 2. And this one is a bit easier for computer, okay? Although we don't like to calculate the eigenvalue, but for computer, calculating the eigenvalue is not too bad. So maybe you can get lambda 2 as a lower bound and then check whether you can find a set of vertices. After taking out all of them, then it becomes disconnected. So this lower bound is still important in many sense. Okay. So that's all I want to deliver, and I will spend maybe another 5 to 10 minutes to sketch the proof of this one. But if you are interested, then let's follow me to understand a bit more about this inequality. Okay. I'm just giving you the whole idea, okay? The proof is not too long, but it takes 1 or 2 linear algebra facts. And if you somehow miss in the talk, you just look at the handout. I guess it is cleaner than what I do. Okay, so G is a simple graph. In order to talk about the kappa, the first step is pick a set S that is part of the vertices, such that G taken out S is disconnected. And this S is the smallest one already, which means the size is equal to kappa G. Okay, so basically we pick the optimal set for kappa G. And the graph will look like this. S, and then this S will connect it to something else. The whole thing is G, but after taking out, you got at least 2 parts. Maybe you got 3 parts. It's also possible. But we're going to say at least it can be 2 parts, right? So let's call that as x1, x2. After taking out S, G will be broken into 2 parts of vertices. We call the vertices as x1 and x2. So let's give them some name. Now let's do the second step. The second step do something is more like an observation, but it says the following. It says lambda 2 of g plus an extra edge is going to be greater than or equal to lambda g, lambda 2 of g. So this is true for any graph. Whatever the graph you have, then just pick one edge which is not inside yet, then add the edge, and the lambda 2 will increase. So in order to talk about the lower bound, let's increase the lower bound. That's fine. So let's try to create edge from G by adding all possible edges between S and V, taking out S. So the edges in between, it might not be that connected, but try to add all edges from S to any vertices outside, from any vertex in S and any vertex outside. So in terms of the Laplacian matrix, it will look like this. It has something on the here, and it is minus j here because O minus 1 from, okay, this part is the S part, and then you can break that into two parts again. This part is x1, this part is x2. Let me call this as L1 and L2. Then we are almost there. So let's look at this matrix once more. This part is H. This part is S. It is basically the structure is the same as G, except for the diagonal entries. And then this part is different. We add a lot of edges from S to outside of edge. From S to outside of S. But after adding that, we know the structure here is O minus 1. Here is O minus 1, which makes it a lot easier to analyze this case. Okay, how about L1 and L2? Again, they have the same structure, but the diagonal entry is a bit different. However, this is the Laplacian of H. So if you just take one row here, row sum is equal to 0. Same as here, is equal to 0. So what does that mean? It means if you just look at the row sum of L1 and L2, okay? So if you only look at the row sum of L1 and L2, then row sum of L1 is equal to the size of S, right? Because there are S numbers of minus 1 here, and plus the row sum of L1, it is become 0. So the row sum of L1 is exactly equal to the size of S. And the same story works for L2 because it's just the same argument. Okay, so we're going to do something wise. I need to look at this vector all the time, but there is some interesting vector which is called U. This vector U is 0 on the part of S, and it is equal to n2 times 1. It is a lot of n2s on x1, and it is a lot of minus n1 on x2. So here is a minus. Sorry about that. Yeah, I'm not going to say that in detail. The point is, let's see. Laplacian h times u is exactly equal to s times u. You can just do the multiplication by yourself and look at that for a while. You'll realize, okay, it is really equal to s times u. This is the first fact. The second fact is u is orthogonal to 1. So in conclusion, lambda 2 of h, let me start from this side. Lambda 2 of g is less than or equal to lambda of h by the second point, and less than or equal to s, because we found an eigenvector which is orthogonal to 1, and this eigenvector is corresponding eigenvalue is s. So s is greater than or equal to the lambda 2 of h, and this one is greater than or equal to the lambda 2 of g. But s is exactly equal to the kappa. So that completes the proof.